Hello everybody, this is the video clip for chapter 3 and we are talking about the applications of the derivative. Okay, for this video clip we are going to concentrate on the curve sketching. However, before we can sketch the curve, we are going to go through several things first. Okay, the first thing is about like to determine in which interval that your function is increasing or decreasing, and then after define like which interval it is increasing and decreasing, we can determine where the function attains its maximum and the minimum values. Okay, and by maximum and minimum we got two kind of max and min. Okay, the first kind is called the relative, okay, or the local max and local min. Another one is called the absolute, okay, or the global max or min. Okay, and actually the maximum and the minimum value, okay, if we don't indicate whether we want to find a max or min, sometimes we can say that it is the extreme values. Okay, and then from that kind of questions we can go over the problem. Okay, some kind of problem, especially this will be the word problems. Okay, that you are going to read some kind of context and then try to optimize something. Okay, in that situation, for example, we want to have a maximum profit or a minimum investment that we are going to pay, that kind of thing. Okay, and then from those kind of problem we are going to go for another concept which is called concavity. Okay, by concavity we will have two kind of concavity, which is concave down and concave up. Okay, so we are going to determine again in which interval that your function is concave down, in which interval that your function will concave up. Okay, and after that we can determine the vertical and the horizontal asymptote. You remember we have been talking about the vertical and the horizontal asymptotes on the first chapter. Okay, and then after that we are going to try to look for the shape of the graph and try to sketch the curve of the given functions. Okay, so that will be something that we are going to go through. Okay, so let's look at the first thing that we are going to go over. We are going to talking about the increasing and decreasing function. Okay, so actually for increasing we are going to say that a function f is increasing on an interval I if your f of x1 less than your f of x2 whenever your x1 less than your x2 in that interval. Okay, so it means that the function value follows the input value. You see, so if your input x1 is less than your x2, then a function value at this point will less than a function value at the second point as well. Okay, so for example this one, you see x1 is less than your x2, right? So here is your f at x1. Okay, y value. There is your f at x2. Then your f at x1 will also less than your f at x2. Okay, and again if you change the x1 and the x2, for example here in this interval, it still follow the same behavior as your input, right? Okay, you see your output follow the same behavior of your input. Okay, so it means that in this interval your function is what? Increasing. You see, and if you look at the graph or the curve carefully, you may see that hey, if we want to draw a graph, okay, but we draw a graph as in, you know, as you write a sentence. Okay, because usually you write your sentence from left to right, right? So we are going to draw a graph that way. from left to right. If you draw a graph from left to right, then you see that the graph is what? Is going up, okay? It's going up like that. So by increasing, it means that as you draw a graph, the graph is going up like this, okay? So here the graph is going up, okay? So on the other hand, if you look at the other one, okay, your f is called decreasing in that interval if your f of x1 greater than your f at x2 whenever again your x1 less than your x2, okay? So for example, if you look at this one here, this can be your x1, this one can be your x2. You see your x1 is less than your x2, right? But your f at x1, which is here, your f at x2, which is there, you see your f at x1, your f at x1 is greater than here, your f at x1 is greater than your f at x2, which is at this level, okay? And if you change your x1 and x2, is still having the same behavior, okay? So this behavior like switch from, you know, this input, okay, x1 less than x2, but your output, okay, just go the other way around. This kind of thing is called decreasing. So it means that in this interval, okay, your graph, your function is decreasing. And again, as you can see, okay, here the graph is what? Is going down. You see, it's going down. So if the graph of a function is going down in that interval will become the decreasing interval of a function, okay? And this one, you see, it turns up again. So it means that along this one, it is what? It is increasing, you see, in this interval. But this one, it is decreasing, okay? So for example, this function, it is this f is decreasing over the interval from b to c, and your f is increasing over the interval from a to b and from c to d, okay, something like that. Are we all right? Okay, so here for the we got a theorem, okay? Why is that we have that theorem? So let's look at this picture again, okay? For the increasing, if you just pick up one point here, okay, let's say this one here, okay, a point on the graph, and then we construct a tangent line, okay, you see that a tangent line along this curve of increasing, it will be a tangent line that doing less than 90 degree, okay, with the positive x-axis, okay? So it means that this tangent line, a slope of a tangent line is positive, right? So this one over an increasing interval, okay, the slope of the tangent line is positive. But what is the slope of the tangent line? It is f prime at that particular point, right? For example, this one at x2 is positive, okay? However, if you look at the other way around, okay, for example here, okay, the slope of the tangent line, okay, the tangent line may be this one and the tangent line may be that one, okay, which is the slope becomes what? A slope here is negative, okay, or your f prime at this point, let's say x2 here is negative, right? So from looking at this kind of thing, the slope of the tangent line, you can also determine whether the function is increasing or decreasing or not, instead of looking at the curve of the graph itself, right? So we got this theorem, okay, and the theorem says that if your f prime over some interval is positive, then your f over that interval is increasing. On the other hand, if your f prime over that interval is negative, then your f over that interval is decreasing. Okay, so for example, if you look at this one, you see that your f prime, okay, it is 2x. All right, so it means that it will be f prime, which is 2x, is positive whenever your x is, sorry, I say positive but I write down negative, right? Sorry. 2x is positive whenever your x itself is positive, right? And your f prime, which is 2x, is negative whenever your x is negative, right? So it means that your f itself is increasing, okay, on the interval from 0 to infinity, and your f itself is decreasing over the interval from negative infinity to 0. Okay, okay, and actually you can, this one is not that difficult to check, right? From the curve, you see this is 0, and from here negative infinity to 0, the graph is going down, you see, as you draw it. So it means that you have an decreasing interval, right? But if you passing that 0, then the graph start going upward, okay, as your x continue to infinity. So it means that we have the increasing interval over there. Okay, so let's look at this one. Okay, this is your f of x equals to negative x plus 2 raised to the power 2 or 3. So it means that your f prime equals to negative 2 over 3 x plus 2 raised to the power negative 1/3, right? Okay, okay, or it is what, negative 2 over 3 x plus 2 raised to the power 1/3, right? Okay, so this one is negative whenever what, this is what, this is negative already, right? So it means that if the whole thing will be a negative value, it means that your bottom must be must be positive, right? Because the top is already negative. So negative over positive, then it will be negative, right, at the end. So it means that your x plus 2 raised to the power 1/3 must be positive. So it means that your x must be greater than negative 2. Are we okay? Are we okay? So it means that from negative 2 onward, okay, this one will be the interval of decreasing. Be careful, because we are now talking about f prime is negative, right? So if we do it here, okay, for this problem, your f prime again, it is this one, right? When is it going to be positive? Again, this is already negative, right? So it means that if you need a fraction to be positive, your bottom must be positive, okay? And your bottom will be, sorry, how come I keep saying a wrong thing? Your bottom must be negative, right? So that negative over negative will end up with a positive value, okay? So when is that your bottom will be negative? So it depends on this x plus 2 raised to the power 1/3, right? So if your x less than negative 2, then the x plus 2 raised to the power 1/3 will be negative, okay? So here, from negative to downward here, it will be the what? Interval of increasing, okay? Increasing. All right, so here don't forget again that we're talking about the one with your f prime is positive, okay? So here is increasing. So the increasing over what? Negative infinity to negative 2, and it is decreasing from negative 2 to infinity. Okay. Okay. One thing that you may need to notice is that, okay, so this one we are going to let you do it by yourself at home. That how about your f prime at negative 2? Okay, this is for the problem B. Okay, how about your f prime at negative 2? What happened there? Okay. Okay, you look it from here, you see that, hey, you cannot plug in negative 2, right, because it is at the bottom. So it means that you cannot find your f prime at negative 2 by this formula. You need to use the what? Use the definition. Remember the limit what of f of x minus f at a over x minus a as your x goes to a. But this one, your a is what? Is negative 2. So what happened? And you see something later on. Okay, right? So now we are going to say that your the point where your f prime equals to 0 or your f prime does not exist. Okay, we have two kinds. The first kind is that your f prime equals to 0. The second kind is that your f prime does not exist, or this x value will call a critical number of that function. Okay, or those x value, okay, is called the critical number of a function. All right, so if you look at the graph, okay, this one is one of your critical, right? Why is that? Because your tangent line is horizontal. Okay, by horizontal it means that your f prime at this point equals to 0. This one as well, you see, this is another one that your horizontal is your tangent is horizontal. So it means that your f prime at the point x2 equals to 0 as well. Okay, and you see that this one is a peak, right? Okay, or sometimes we call it a hill. Okay, this one is a hill. By a hill, it means that if you consider the neighbor of that point, okay, if you consider a neighbor of that point, that peak or that hill will be the highest value, okay, among those nearby. Okay, only nearby. All right, this one as well, you will see that, hey, this one is like a valley. Okay, so it means that if you consider only nearby point, okay, a neighbor of that point will be the one that the lowest, okay, attain a lowest value among all neighbor. Okay, so this one sometimes called a valley. Okay, so a hill correspond to a so-called local maximum. Okay, or sometimes instead of local we use relative. Okay, and this one correspond to a local minimum. Okay, a local minimum. All right, however, a local max or local min may occur like this. Okay, you see, this one can be a hill as well, a local max. Okay, this one can be a valley as well. This one can be a local min. However, at this particular point, okay, a derivative, which color should we use? Among this particular point, a derivative at those points does not exist, remember, because it got a corner. Okay, or sometimes a corner can be this bad. Okay, a corner can be this one, a corner can be like that. Okay, depends on what kind of corner that you're talking about. Okay, but it's still a hill. You see, it's still a hill, and if you flip it, it becomes a valley. Okay, So how are we going to determine which one is a local max, which one will be a local minimum? Okay, it depends on the tangent line. You see, this hill, how can it becomes a hill? Okay, around that point, okay, the tangent change from positive tangent to a negative tangent. You see, but around the local mean, a tangent change from positive, okay, sorry, change from negative to a positive tangent. Okay, so it means that we have the so-called a first derivative test. A first derivative test saying that if your x equals to c is a critical number, so don't forget what was the critical number. We got two kinds, right? The first kind is that your f prime at that point equals to 0, or at this point does not exist. Okay, the f prime. All right, then the first thing is that if your f prime or the tangent line, okay, the slope of the tangent line changes the sign from positive to negative. So from positive it means it going upward, to negative, so it means that you got a hill, right? So your f at c attain its local maximum. And if your f prime change from negative to positive, so it go like a valley like that, so it means that your f at c attain a local minimum. Okay, so you usually draw a tangent line like that to so that you just remind yourself, okay, what it corresponds to at that point. All right, so let's take a look at this one. If you want to find a critical number and also determine a local max and a local min of all these functions, okay, so first you need to find your f prime. Your f prime is 12x cubed minus 12x squared. Okay, so this one it is just a polynomial, right? So your f prime exists, okay, for each and every value of x in a real number. So the critical number will have only the first type, okay, which is your f prime at that point equals to 0. So you solve for a critical number first. Okay, so critical number, this one you need your f prime to be 0. So it means that your 12x cubed minus 12x squared equals to 0. Okay, and actually you may say that, hey, I would like to just get rid of 12. Okay, that would be one thing to do. However, for this chapter I encourage you to do it the longer way, so that you don't cancel anything, you just keep it, okay, and just pull out all the common factor like that. Okay, so a common factor will have 12 and x squared, right? Okay, and then you see that your x, okay, the critical is that your x can be 0 and your x is 1. Okay, so you got two critical. So let me insert one more page. Okay, you got two critical. Now to determine whether the critical is really a local max or local min, you need to look for the sign, okay, of your f prime. So let's see, this is 0 and 1, and then this one is the sign of your f prime. Okay, here's your f prime, right? So you need to look for the sign of your f prime. Okay, and usually we are going to look at your f prime as the factor like this, okay, to see the sign. That will be a little bit more easier. Okay, and then what you are going to do is like to plug in some number in the interval, okay, that is not your critical number. For example, this one is, this 1 and 0 are your critical numbers, right? So here is like one interval that you need to determine the sign of your f prime. So you can like choose one number among this interval and just plug in, like one number will be good enough. For example, if you plug in 2 into here, you know that this one is a 4, so it's positive. This one 2 minus 1 is a 1, so it's positive. And actually you don't really want to know like the number, but you just want to know whether it's positive or negative. So it's all positive, right? So this one, the sign of your f prime is positive. Okay, and then this one you can plug in, for example, 0.5. Okay, so here square is positive, 0.5 minus 1 is negative, right? So everything become negative, so here is negative. And then here you can plug in -1. So -1 will be, again, don't forget, a square always positive, right? So -1 minus 1 will be -2, which is negative. Okay, so positive negative becomes negative. Okay, so it means that on this one your graph is going down, this one is still keep going down, but then it changed to go up. Okay, at this point, so it means that at this point you got a valley, right? But you have no hill. Okay, so it means that here your f, okay, actually you can determine that your f is, let's do it the long way. Okay, your f is actually decreasing on which interval? On the interval from -infinity to 0 and 0 to 1, and your f is increasing on the interval from 1 to infinity. Okay, so it changed the sign here at 1. Okay, it changed the sign here, so it means that your f at 1, which is what, 3 1/4 minus 4 1 cube, which is -1, is a what? A local minimum, okay, of this function. Okay, and your f has no local max. Are we all right? Okay, for this one your f only has a local minimum but no local maximum. Are we all right? Okay, and if you look at it, roughly speaking, okay, roughly speaking, it seems that your curve like keep going down. Okay, keep going down to 0, and then from here it going upward like that. Okay, however we still cannot sketch the exact curve. Okay, because we don't have any other information, but we just roughly speaking knowing that it just going down and then it going up here. Okay, but we don't know like how it go down. Okay, it may go down like this then go up. Okay, or it may go down like that and then go up, depends on the other thing which is called the concavity. Okay, that we are going to determine later on. So let's look at this one, the second problem. What's your f prime? Your f prime, this time you need to find you need to use the what, the product rule, right? It is the first derivative of the second plus the second derivative of the first, which is the x, right? So a derivative becomes what? Becomes 1. Okay. So here you are going to again pull out a common factor. So you have -x plus 1, we get. Okay, and don't forget that the exponential always positive. Okay, and this one is a polynomial, so it means that this one exists for each and every x in the real number. Okay, so again a critical value will contain only the first kind, okay, which is f prime equals to 0. Okay, so if your f prime equals to 0, it means that your e to the -x and then this one equals to 0, but this one cannot be 0, right? So it means that only this part that can be 0. So it means that your x is 1, right? So you are going to again look at the sign of your f prime, okay? And it will the only thing that you need to concentrate is at x equals to 1. So for example, you again has two intervals, okay, that you need to consider. The one right here, so you can just pick up 2 and then you plug in, okay. This one's always positive, right? This one is like negative 2 plus 1, so it's negative. So it means that on this the one the interval beyond 1, it is negative, right? And this one you can plug in 0, that is easy, right? So if you plug in 0, this is positive, this is always positive, so it means that among here it is positive. So the graph, okay, the graph will going upward, okay, and then going down like that. So it means that this one has a hill, okay. So we can conclude that your f is increasing, okay, over the interval from negative infinity to 1, and your f is decreasing over the interval from 1 to infinity, okay. This one decreasing, and your f at 1, okay, from the side of your f prime, it means that your f at 1 is a local maximum. All right, okay. So you can say that your f at 1 is actually what? It's actually 1 e raised to the power 1, which is 1 over e, is a local maximum of this function. But your f has no local min. You see, this one has no local min, okay. It's not like the previous one. The previous one, you say that your f has no local max, okay. So it means that your graph somehow look like that, okay, or it may look like this, okay. It depends, but it has only one hill, okay. So we still don't know exactly the shape of the curve of the curve, okay. We need to have some other information later on. Let's look at one more example, okay. This one, your x squared minus the absolute value of x plus 1, okay. So here actually it is the x squared minus x plus 1 if your x is positive, and it is x squared minus x plus 1 if your x is negative, okay, because of this absolute value, okay. So don't forget that the absolute value can be what? Can be just x itself if your x is positive, and it can be negative x if your x is negative, okay. So to find the critical value, you need to find your f prime, right? Okay, so if your x is positive, then your f prime is just simply 2x minus 1, and then you need your f prime to be 0, right? Because this one again exists, okay, for each and every x that is positive, right? So it means that your x can be 1/2, and 1/2 it is positive, so this one can be one of your critical. If your x is negative, then your f prime, you're choosing this one, right? This is a plus, so you have 2x plus 1, and then make it equals to 0 again, because this one again exists for each and every x that is negative, right? So it means that your x is negative 1/2, and negative 1/2 is really a negative number, so this one can be another critical, okay. And don't forget, here you got one, you got two functions, okay, and one junction at 0. So at 0 you need to really take care or looking at the derivative. Okay, so how about at x equals to 0, you need to find this one f of x using a definition, right? So this one, oh, because a 0 is a junction, so you need to look at the left hand side and the right hand side limit. Okay, so by the left hand side limit, it means that your x is negative, right? So we are going to use the lower formula, which is a positive one. Okay, and then minus f at 0. F at 0, it is here, which is 1, right, over x minus 0, which is x. So the 1 and the 1 cancel, and because your x is negative, then this one cancel as well. Okay, so you end up with a limit as your x goes to 0 on the left of x plus 1. Okay, which is what? Which is 1. Okay, however, if you look at the other way around, to 0 on the right, okay, so it means that your x is positive, right? Okay, so if your x is positive, you use the upper formula, which is the one with negative. Okay, but then this one are the same, right? Okay, your f at 1 is your f at 0 is still 1. So here the 1 and the 1 cancel, the x cancel once, so you end up with a limit as your x goes to 0 on the right of your x minus 1, which is negative 1. They are not the same. What does this mean? So it means that your f prime at 0 does not exist. Okay, so it means that now your critical number of this function f are 1/2, negative 1/2, and 0. So you got 3 of them, and right now for this function you got the one that your derivative does not exist as well. Okay, so let me write down the f prime again so that we will easily look at the the side of your f prime easily. Okay, so this one is your f prime, and we need to look at the side of your f prime in between all these critical number, right? So here again, it is the side of your f prime. Okay, so you keep write it this way so that it remind yourself that this one is only the side of f prime, not the f itself. Okay, so for example, this one you can say, hey, if it is 1, then what happened? So you have 2 minus 1, which is positive, right? Okay, if this one is, let's say, like this is 0.5, right, you can use 0.1. Okay, so it will be 0.2 minus 1, so negative, right? So we have negative here. This one you can say again, negative 0.1. So you plug in here, you have negative 0.2 plus 1, so it is positive, right? And then this one you can use what? Negative 1. We got negative 2 plus 1, which is negative. Okay, so look at it carefully, which formula that you are going to use. Okay, so on this part we use this formula here, and on this part we use the formula up there. Okay, so it means that you are the curve look like this, right? So it's going down, and it's going up, and then it's going down again, and then it's going up. Okay, so what does this mean? You got two valleys. You see, a local mean occur here, and there a local max occur here. Okay, so look at it carefully. We didn't say that this one is a local max and a local mean value, but we say that it occur at this x value. Okay, so we would like you to write down by yourself, okay, whether your f is increasing over which interval, and your f is decreasing over which interval. Okay, however, we can say that your f at negative 1/2, okay, which is what? Look at your f again, it is x squared, right? So you have negative 1/2 square minus the absolute value of 1/2 and then plus 1, which is 1/4 plus minus 1/2 and then 1, so you got 4 2 4, right? So you have 3/4. So this one is a what? A local mean occur at the point x equals to negative 1/2, right? So this one is a local minimum value. Okay, it's one of them. And then another one is f at 1/2, which is 1/2 square minus the absolute value of 1/2 and then plus 1. But it will be the same thing, right? Right, it will be the same value. This one is also a local minimum value. And f at 0, which is what? F at 0, remember, it just simply 1, right? Is a local maximum value. Okay, so for this function you have both local min and a local max. Okay, and a graph look like that. Okay, however, you know that this one at this point derivative does not exist, so you know that at this point it must be a corner. Okay, so somehow it may be look like that, we don't know, or it may look like this one. Okay, we yes, what should we say, it may look like this one. Okay, we don't really know what the shape is. Okay, we need to attach with some other information in order to know the shape of the graph. Are we all right? So we are going to stop this video clip right here. Okay, so on this video clip we know how to find the critical numbers of a function, and we know how to determine whether at that critical number your function attains a local max or local min by using the first derivative test here. Okay, the first derivative test here. So we should stop right here first, and then we are going to continue the next one with some other extremum value. So we'll see you then. Bye bye.